Our fourth and final shuffle for today is also a judicious push-off pairs with the stacking similar to the previous shuffle, Shuffle 31, except that the final two piles will be stacked with the left pile on top of the right. So let's go ahead and illustrate that and derive the permutation associated with this shuffle. So we begin with our ordered packet 1 through 8, and we perform the shuffle. So push-off pairs is where you just push off the top two cards without rearranging the order of those two cards relative to each other. You push off the next two. You push off the next two. Finally, that leaves us with 2 that would make up the fourth pile. So we have piles 1, 2, 3, and 4. And so we can see the stacking requires us to do the following. This is pile 4. It leaps over pile 3 and gets stacked on top of pile 2. Pile 3 leaps over pile 2 and gets stacked on top of pile 1. And now we're going to stack the left pile on top of the right. So what is the new ordering that results from this shuffle? Well, it's the following: 5, 6, 1, 2, 7, 8, 3, 4. So writing this in Cauchy's two-line notation, we obtain the following. The top row, as always, is just 1 through 8. The bottom row will be the new ordering: 5, 6, 1, 2, 7, 8, 3, 4. And we can convert two-line notation to cycle notation, in other words, one-line notation, as follows. We see that 1 goes to 5, so there's an arrow from 1 to 5. 5 goes to 7, so there's an arrow from 5 to 7. 7 goes to 3, so we have an arrow from 7 to 3. And 3 returns back to 1, so that completes that cycle. And in particular, it is a 4 cycle, since it consists of 4 position values. In a similar fashion, let's see what happens with 2. 2 gets sent to 6, so we have an arrow from 2 to 6. 6 gets sent to 8, so we have an arrow there from 6 to 8. And then 8 goes to 4. We can see that with the arrow. And then 4 returns back to 2, completing a second 4 cycle. And that accounts for all 8 digits. So if we color code our digits, we obtain the following. Recall that positions 1, 4, 6, 7 are color-coded black, and positions 2, 3, 5, 8 are color-coded red. And as we've talked about, this will aid us in perceiving the effect of shuffles on Bessey sequences of order 8. So we see that black 1 goes to red 5, which goes to black 7, which goes to red 3, which wraps around and goes to black 1. Red 2 goes to black 6, which goes to red 8, which goes to black 4, which gets sent back to red 2. So each value gets sent to a value of the opposite color. And when that happens, inversion has occurred. Now, this simply means that the cards that originally began in positions 1, 4, 6, 7, so in these 4 positions, 1, 4, 6, 7, those cards get moved to positions 2, 3, 5, 8 in some assignment. Okay, and in a similar way, the cards that originally began in positions 2, 3, 5, 8 get moved to positions 1, 4, 6, 7. And since inversion occurs, we should be able to detect that using our Bessey sequence 1, 0, 0, 1, 0, 1, 1, 0. Because apparently this shuffle should invert this sequence. What does it mean to invert the sequence? That means that zeros and ones switch places. So let's see if that actually occurs. So we're going to perform our shuffle. So we push off the top 2, push off the next 2 as a second pile, the next 2 as a third, and the final 2 as a fourth pile. And the stacking is the fourth pile gets stacked on top of the second. The third pile gets stacked on top of the first. And then the left pile is stacked on top of the right. Okay? So is it true that inversion has occurred? Well, inversion will have occurred if we now have the sequence 0, 1, 1, 0, 1, 0, 0, 1, which we do. And it's important to note that the zeros and ones in our packet here, all of them have moved to new locations, as indicated by our cycle notation of this permutation. There are no fixed points whatsoever, so every single card is moving to some new location according to these assignments here. And also note that this particular shuffle is of order 4 because it's a product of 4 cycles. That means you need to perform this shuffle 4 times to return the packet to its original order. And finally, taking a look at the shuffle diagram for shuffle 32, we find the following. 1 goes to 5, which goes to 7, which goes to 3, which wraps around to 1. So that means if we start at 1, we should have an arrow that goes from 1 to 5, 5 to 7, 7 over here to 3, and then an arrow from 3 to 1, completing that cycle. And we say that those 4 values are members of the same orbit. In a similar fashion, for the second 4 cycle, we see that 2 goes to 6, which goes to 8, which goes to 4, which gets sent back to 2. So that means if we begin at 2, there should be an arrow from 2 to 6, which there is, from 6 to 8, which we have right here, from 8 all the way down to 4, and then from 4 back to 2. And that completes that 4 cycle. And those 4 values represent a second orbit. And as I mentioned a few moments ago, shuffles 30 and 32 are inverses of one another. If you perform them in succession, they will return an ordered packet to its original order. Why don't we just go ahead and illustrate that quickly, since these two do constitute an inverse pair. So if we begin with our ordered packet, so that we can keep track of what effect these shuffles will have on the starting packet, what we have just observed is that if we perform, let's say, shuffle 30 first, followed by shuffle 32, it should return this packet back to its order 1 through 8. And vice versa, if you perform shuffle 32 first, followed by shuffle 30, it will also return or reset the packet to its original order. So why don't we go ahead and perform shuffle 30. So it's a push off pairs, so we're just pushing off pairs without changing the relative order of the cards within each pair. And then if you look at shuffle 30, it's the top row on the right. We're stacking the first pile on top of the third, the second on top of the fourth, and then we're stacking the right pile on top of the left, like so. Now, of course, we're going to get quite a mixture of cards here, right? We get 3, 4, 7, 8, 1, 2, 5, 6. This is very different than 1, 2, 3, 4, 5, 6, 7, 8, okay? But what we have just seen is now if we perform shuffle 32, it will straighten all of this out and take us back to our originally ordered packet 1 through 8. Now, if you look at the differences between these two shuffles, I don't think it's clear, and probably would not be clear to most anyone, that these shuffles should undo the effect of each other. I don't think that's clear at all. So shuffle 32, we begin the same. We push off pairs. But this time the stacking is different. We're going to stack the fourth pile on top of the second, the third one on top of the first, and now we're going to stack the left pile on top of the right. And apparently this will perfectly undo the effect of shuffle 30, which it does. It returns the packet to its original order 1 through 8. Okay, as an application, I have here